Yes. Am I audible? Hi, good evening all. Am I audible? Let me know whether I am audible or not. Yes. So put it in the comment box. Am I audible? Hello? Yes. Am I audible? Yes. Good evening all. Welcome to Goscore Learning. We are the fastest growing edtech in GCC. Our aim is to provide education for all. Okay, so welcome to the physics session. My name is Rahul. I am from the physics department of Goscore. So today we are discussing the 8th chapter, electromagnetic waves. Electromagnetic waves of grade 12 physics. Okay, so what's the peculiarity of this chapter? So now this is February last, right? So February mid, on next week you are going to start writing your board exam. So currently all of you have finished. I think all of you have finished the portions in physics, not only in physics, in every subject. So now you know. So what is the peculiarity of this chapter, as you have covered this chapter? So we can go wind up this chapter in this section itself. So you know what is the property peculiarity of this chapter. This is the one of the smallest chapter in grade 12 physics, right? So even though it is the smallest chapter by content, it is the smallest chapter, but this chapter includes in a group that consists of ray optics, wave optics. So electromagnetic waves, EM wave means electromagnetic waves. So EM waves, ray optics, wave optics. So these are consisting a group, and in exam there will be 18 marks questions from this group. So even though this chapter is a small one, the marks weightage is very high for this chapter. Any other group didn't have this much of weightage, less than 18 only, like 17, 16, 15, like that. Okay, so this EM waves, even though I am written over the EM waves, in exam you have to write electromagnetic waves, right? Okay, don't write EM waves. So EM waves, ray optics, wave optics, consisting this group consisting three chapters, and out of from these three chapters, 80 marks question will be there. So as everyone know, there is no equal division. 6 marks from this chapter, 6 marks from this chapter. This will not happen. Maybe majority of the question can be asked from ray optics or wave optics, or majority can be asked from EM waves. So what I am telling is, even though it is a small chapter, there are 80 marks question from this group. Okay, so very important, and we can ensure each mark that is asking from this chapter, because this is very easy chapter. So this is the one among the easiest chapter in grade 12 physics. Okay, so we can discuss this chapter today. So what are the contents in this chapter? Displacement current, electromagnetic waves, properties of electromagnetic waves, EM waves, and electromagnetic spectrum. So these are the major contents that include in this chapter. So if you thorough with this topic, means you can score full mark for the question that is asked from this chapter. Okay, are you ready? Can we move to the content of this chapter? Yes. So displacement current is the first topic, right? Okay. So before entering into the chapter, we have to collect some ideas from the previous chapters, chapter 4 and chapter 6. So what's the name of the chapter 4? Moving charges and magnetism, right? So in that chapter, what you have learned is, whenever a charge is moved, whenever a charge is having a velocity, set a velocity, it will be creating current. Or moving charge, what is moving charge? It is electric current, right? So electric current produces magnetic field. Electric current produces magnetic field. That you have learned in chapter 4. It's not only this chapter, in grade 10, the last chapter, magnetic effect of electric current. So you have learned that electric current, moving charge, will produce magnetic field. And what you have learned in chapter 6, which is electromagnetic induction, a time varying magnetic field, or magnetic field changing with time. So time varying magnetic field will give rise to electric field. A time varying magnetic field will gives rise to electric field. What is that? Is electromagnetic induction, right? So whenever there is some change in magnetic flux, there will be a current. Electric field will be produced. So that is what you are discussing in chapter 6. And so in this chapter, what we are discussing is just opposite. What about time varying electric field creating a magnetic field? What about a time varying electric field creating a magnetic field? So as you know, a time varying magnetic field, a magnetic field that is varying with time, which is producing electric field, vice versa is also possible. That is what we are going to discuss today. Okay, so a time varying electric field will also produce a magnetic field. Time varying electric field will produce a magnetic field. Did you got it? Did you get it or not? Yes, then we can move to the chapter. Okay, so if you have any doubts related to the topic that I have mentioned, any terms that I have mentioned in this chapter, in this class, please comment below. Okay, so we can move Maxwell's contribution. Okay, so Maxwell introduced the idea of displacement current and modified Ampere's circuit law. So in fourth chapter you have learned Ampere's circuit law, right? So here we have to recollect it. So here there is a new term for you, displacement current. What is displacement current? As you know, displacement current, that is a topic that we are discussing in this chapter itself. So we can know more about the displacement current. Okay, so he modified, Maxwell introduced the idea of displacement current and modified Ampere circuit law. Why he modified Ampere circuit law? There is an inconsistency with Ampere circuit law. So there is a inconsistency with Ampere circuit law. That inconsistency we can discuss today. Okay, so what is the problem with Ampere circuit law? Before that we can move to what is Ampere's law? What is Ampere's law? Means Ampere circuit law. Okay, so that you have learned in grade, sorry, chapter 4 itself, not grade. Okay, so what is Ampere's law? Closed integral b dot dl is equal to mu 0 I. So this is what is Ampere circuit law, right? So what do you remember the top definition? What is the definition for Ampere circuit law? Read it, read it. What is the definition? The line integral of D means magnetic field. The line integral of magnetic field along any closed path. That's why I have introduced closed integral. Okay, so line integral of magnetic field along a closed path. So closed line integral equal to closed line integral b dot dl. So closed line integral is equal to, so both are vectors. Okay, so closed integral b dot dl is equal to what is mu 0 times the total current, mu 0 times total current. So mu 0 I. So this is what is Ampere circuit law, right? So there is a problem with this equation. There is a problem with the equation. That is what we are going to discuss. Okay, so the line integral of magnetic field along a closed path is equal to the mu 0 times current, total current enclosed by the path or enclosed by the closed circuit. Okay, so this is Ampere's law. So what is the problem with this law? We can the problem was corrected by Maxwell using displacement current. Okay, the problem was corrected by Maxwell using displacement current. Then what is the problem? We till didn't discuss that problem yet, right? So what is the problem? Do you know about what's the inconsistency with Ampere circuit law? What's the inconsistency? For that we can check with the circuit. Okay, so what is this? This is nothing but the battery is connected. Okay, here there's a battery. Okay, and this is two plates, parallel plate capacitor. Okay, two parallel plate capacitor I have connected to a battery. Okay, two parallel plate capacitor I have connected to a battery. So this is positive terminal of the battery and this is negative terminal of the battery. Okay, so when the switch is turned on, what happened? What happened? Current will flow and positive charge, as this plate is connected with positive terminal of the battery. So this plate will be charged positive, right? So this plate will be acquiring positive charge. And what about this? What about this plate? Whatever the other plate. So this is connected to the negative terminal of the battery, right? Negative terminal of the battery. So that what kind of charge it will be obtaining? So this will be obtaining. Sorry. Okay, this will obtaining negative charge, right? So negative charge. Is it okay? So one plate is connected with the positive terminal, other plate is connected with negative terminal. So they will positively and negatively charged. There will be positive and negatively charged plates respectively, right? Is it okay? So as we know, what you have learned in chapter 4. What is we have learned in chapter 4, moving charges and magnetism. Whenever there is a current flow, charge flow, whenever there is a charge flow, there will be magnetic field around it, right? There will be magnetic field around it. So around this straight conductor, there will be magnetic field. As you know, the magnetic field around a straight conductor can be used by can be found out used by application of Ampere circuit. What is we are discussing? Closed integral B dot dl is equal to mu 0 I. So here I we can find using the current in the circuit. Okay, so this magnetic field can be easily find it out by this formula. So magnetic field around a straight current carrying conductor, you will be getting B is equal to this will be the formula mu 0 I divided by 2 pi r. This will be the final formula. The derivation is within the fourth chapter itself. Okay, you can refer that chapter. So this will be the final formula. Magnetic field B will be equal to mu 0 I by 2 pi r. This is just the application of Ampere circuit law. Application of Ampere circuit law for a straight current carrying conductor. So this will be the equation. So here there will be a magnetic field here, and this is another straight conductor. So here there will be another magnetic field, which means the current will give rise to another magnetic field here. B will be equal to same equation as it is a same conductor, mu 0 I 2 pi divided by 2 pi r. This will be the magnetic field over here. So whenever we are taking a magnetic needle and place it over here on here this point, if you are placing a magnetic needle over there near to the straight path, there will be a deflection in the magnetic needle because of this magnetic field. And whenever I am placing another magnetic needle over here, there will be a deflection in that needle because of this magnetic field. Could you follow? Yes. Then, so when I am placing, I am marking three region. Okay, so in the first region, I have seen that magnetic field over there because magnetic needle is deflected. In the third region also, we can see that there is a deflection in magnetic needle because there is a magnetic field. Okay, so in the second region, if I am applying Ampere circuit law, so what is the equation? I will write it here. Applying Ampere circuit law, B dot dl is equal to mu 0 I. So here I can imagine an Ampere loop. That is, for the application of Ampere circuit law, we have to imagine an Ampere loop, right? So here, what is the current in this Ampere loop? What is the current in this Ampere loop? As you know, these are two parallel plate capacitor. So this is the region in between the plates of a capacitor, right? As you know, in between the plates of a capacitor, there is no metallic conductor. There is no metallic conductor. It is an dielectric medium will be present, right? So there is no metallic conductor, which means there will be no current flow. So in between the plates, there is no current flow, which means this I over here will be 0. So magnetic field in the second region means between the plates of the capacitor. Between the plates of a capacitor in the second region, there is no magnetic field given by Ampere circuit law. How we get that? By the application of Ampere circuit law, we have to get closed integral B dot dl is equal to mu 0 times I. But what is I here? I here is 0. Why it is 0? Between the plates of a capacitor, there is no metallic conductor. It's a dielectric medium present in it. Maybe air or like something like that. So there is no metallic conductor, which means there is no current at all. So there is no current means the magnetic field will be 0. But there is a problem. So this is the theory that we have. And when I am placing a magnetic needle over here, you can see a deflection. We can see that deflection because there is a magnetic field, right? But according to Ampere circuit law, there is no magnetic field at all. But when we are having a magnetic needle over here, that's not look like a magnetic needle. Okay, imagine this as my magnetic needle. Okay, so when I am placing this magnetic needle in between the place of this capacitor, I can have a deflection in the magnetic needle. But according to the equation that we have, there is no magnetic field at all. So this is the inconsistency with Ampere circuit law. So this is the inconsistency with Ampere circuit law. So Maxwell found this inconsistency and he had to correct it, right? So whether by Ampere circuit law there is no current, but Maxwell corrected this Ampere circuit law. As there is a magnetic field, there should be a current, and Maxwell called that current present in between the plates of a capacitor. Maxwell called that current that lying in between the plates of a capacitor as displacement current. What is it? Here there is an inconsistency. That's why magnetic field, according to theory given by Ampere's, we got it as 0. But there is a magnetic field, and Maxwell found that and he corrected it. and there should be a current. Whenever there is a magnetic field, there will be a current, right? Only current can give rise to a magnetic field. Whenever there is a magnetic field, definitely there will be a current. So as there is a deflection in the needle, there should be a magnetic field, which means there should be a current. And that current present in between the plates of a capacitor is called by Maxwell as displacement current. Okay, what is the quantity? Displacement current. Displacement current. Did you get it? And denoted by the letter, sorry, can be denoted by the letter either capital ID or small ID, displacement current. Okay. So what is the new quantity that you have got now? That is displacement current denoted by the letter ID, displacement current ID. It have the same dimension as that of current. Okay, it have the same dimension as that of current, that of the conventional current or conduction current. Okay, what is that? Conventional current. What is conventional current? The current that we know till now is because of the flow of charge carriers, either positive charges or negative charges or any ion. The current that we know is only because of, till now what we know about current is, it is because of charge flow of charges, either positive or negative charges. So that is what is known as conduction. Conduction of charges creating current. So that is why it is known as conduction current. What is that? Conduction current. Okay. What happened? Yes. What is that? Conduction current. Conduction current means denoted by the letter IC. Okay, denoted by the letter IC. Conduction current can be denoted by the letter IC. So what is conduction current? The current, what we know about till now, what we know about current, that is conduction current. The current due to the flow of charges, that is conduction current. That's why it is known as conduction of charges. So it is named as conduction current. And what we have found it now? It is displacement current. What is displacement current? The basic definition that we can give on the basis of the current that lying between the plates of a capacitor is displacement current. We know that it is not enough. Okay, we can discuss in detail what about displacement current. Okay, so what is displacement current? Displacement current is denoted by the letter ID. Is that enough? No. Okay, it's not enough. It is the current which is produced between the plates of a capacitor. It is the current which is produced in between the plates of a capacitor. So that's in the first definition. Okay, so the given conduction current will be converted into displacement current inside the capacitor. So you know about conduction current. Okay, what is the conduction? Yeah, the given conduction current that is giving from current that is getting from the conduction current, it will be converted. Conduction current will be converted into displacement current, and this is the key point. The current due to changing electric field. Where is the electric field? Look at here. So here there is a positive charge, right? Here in this opposite plate there is a negative charge. Obviously there will be an electric field directed from positive to negative, right? So this electric field is creating that displacement current. Okay, so here what I am applied is a battery, right? You know that capacitor provides infinite resistance to a DC current. So here we have to replace the battery with an alternating current. But initially I didn't do like that, because then only I can ensure that this is positive charge and negative charge. If I am giving alternating current, it will be alternatively changing. That polarity alternatively changing, then it will be hard to explain. So that's why I am giving a battery in the first. Okay, now we can go with alternating current. Okay, so what happened if I am giving an alternating current? The direction, this will be positively charged in the first half, negatively charged in the first half, and reverses, negatively charged in the second half, positively charged in the negative second half. So that electric field will be alternatively changed. The direction of current changes, which means the electric field will be, direction of electric field will be also alternatively changes. Got it or not? Understood? Okay, so this is very important concept. That's why I took time to explain it. Okay, so here electric field is there, which is varying continuously. If I am applying an AC current, that electric field will be varying continuously. So the source of the displacement current over here is because of this electric field, varying electric field, time varying electric field. Now you got the definition. The current due to changing electric field, time varying electric field. So now what we have discussed in the beginning, as I told you in this chapter, what is that? Yeah, this chapter, magnetic field changing with a time varying magnetic field giving electric field. That is what I learned in electromagnetic induction, and I told you in this chapter we will be learning a time varying electric field will give rise to a magnetic field. So we have found it then. We have found it that. What we have found? What we have found? A time varying electric field. A time varying electric field. Here it is, because we are applying AC current. So a time varying electric field will giving a time varying magnetic field. That is the source of, and that time varying magnetic field creating displacement current. So it is the current due to changing electric field. So a changing electric field will giving a time varying electric field is giving a time varying magnetic field. Whenever there is a magnetic field, there should be a current, and that current is displacement current. Get it or not? Got it or not? Got it or not? Could you follow? So as I told you in the previous classes in the moving charges and magnetism, as I mentioned, whenever there is a magnetic field, there will be a current. So here this time varying electric field is producing magnetic field, time varying magnetic field, and that time varying magnetic field is giving the source of that time varying magnetic field is that displacement current. Okay, so in simple words we can say like that the displacement current is produced because of time varying electric field or changing electric field. This is the key point. Okay, don't skip this point. This is the key point. The time varying electric field that lying between the plates of a capacitor is giving rise to the displacement current, and the conduction current that we have given is converted as displacement current. Okay, so there is a formula for displacement current, and the derivation is not included in our syllabus, so it is beyond the scope of our syllabus. So we can simply mention it. So ID, displacement current, is denoted by the letter ID, is equal to epsilon 0 d phi by dt. So the derivation of this equation is not a lengthy one, it's a small one, and even though it is not included in our syllabus, so that we can just simply mention the equation only. Okay, so the time varying electric field is giving what? Giving the displacement current. Okay, yes, it's the box. Let it come. Yeah, no hurry. Okay, so this is the expression for displacement current. ID is equal to epsilon 0 d phi by dt. Okay, we can move. So this is an expression. ID is equal to epsilon 0 d phi by dt. As you know, d phi e by dt. It should be there. Okay, d phi e, electric field should be there. Okay, d phi e by dt, changing electric flux. Time varying electric field is giving the displacement current. Okay, so some more points. Yes, the total current is the sum of conduction current. What is conduction current? IC and displacement current ID. That is, I is equal, total current in the circuit is equal to sum of IC plus ID. Got it or not? Okay, so the source of magnetic field is not just IC. What is IC? Conduction current. What is ID? Displacement current. So source of magnetic field. So source of magnetic field means whenever there is a magnetic field, there should be a current, and that current I is equal to IC plus ID. Oh, okay, now we got it. So remember the formula. Total current now become not only conduction current, it includes displacement current also. So whenever there is no change in electric field, there will be no displacement current. Whenever there is a steady current, there is no displacement current. Whenever there is a changing electric field, changing current, non-steady current, then only there will be a displacement current. Okay, you got it or not? Okay, so Ampere-Maxwell law. So that is modified Ampere circuit law. Okay, so modified Ampere circuit law, or it is also known as Ampere's Maxwell law. So as I told you, Maxwell corrected the inconsistency with introducing displacement current. What was the inconsistency? Do you know it? Don't you know? Then scroll a little bit back. There is a definition. Okay, so what is inconsistency? Is there in the life? Okay, so a few minutes before I have explained it. Okay, so Maxwell modified Ampere's law by introducing displacement current. So this is called Ampere's Maxwell law. So you have to, the statement is like that only. There is no lengthier definition for Ampere's Maxwell law. This is the basic. This can be written as Maxwell modified Ampere circuit law, or Ampere's Maxwell law. Okay, so we can, not only this one, we can write some equation also. Okay, so as you know, the total current in the circuit is equal to sum of conduction current plus displacement current. Whenever there is a steady current, displacement current will be 0. Here there should be a varying current. There should be a varying electric field. Then only displacement current will be 0. Okay, so what was our Ampere circuit law? What was our Ampere circuit law? Before that, I can write the expression for I is equal to IC plus, what is ID? Epsilon 0 d phi by dt. Okay, this d phi e by dt. Okay, electric field. Okay, so IC plus ID means d phi e by dt. Now, what was our Ampere's law? Closed integral v only consider, sorry, in Ampere circuit law, in Ampere circuit law, he have only considered about conduction current, and Maxwell introduced the displacement current and fixed that inconsistency. The logical inconsistency was corrected by Maxwell by introducing displacement current. Okay, so we can give the substitution for ID. So this will become closed integral b dot dl is equal to mu 0 IC plus mu 0, what is ID? Epsilon 0 d phi E by dt. So this is the modified Ampere circuit law. This is the modified Ampere's circuit law. Okay. So this is the modified Ampere circuit law. Important one. Okay. So displacement current is important. Okay. So closed integral B dot dl is equal to mu 0 IC plus mu 0 epsilon 0 d phi by dt. Got it or not? Got it or not? Understood? Yes. So then Maxwell's equation, even though it is not included in our syllabus in textbook, rationalized textbook, these equations are there. So we can just mention them. Okay, first one is Gauss's law for electricity. That you know. What is Gauss's law for electricity? That equation. Sorry. Yes. What is my ink? Yeah. Closed integral electricity, right? So closed integral E dot dA is equal to, what is that? Mu epsilon 0. No. Q by epsilon 0. 1 by epsilon 0 times the net charge enclosed by the surface. The electric flux around a closed surface is equal to 1 by epsilon 0 times 1 by epsilon 0 times the net charge enclosed by the surface. That is Gauss's law for electricity. That you know. So then what about Gauss's law for magnetism? It is not in our syllabus, but even though we can just mention that, I'll explain the logic behind that. Closed integral B dot dA is equal to 0. Why it is 0? Magnetic monopole cannot exist. North pole means magnetic positive charge. Magnetic positive charge. South pole means magnetic negative charge. So whenever there is a magnetic north pole, definitely there will be magnetic south pole, which means magnetic monopole cannot exist. This is what we have discussed in chapter 5, magnetism and matter. Okay, so magnetic monopole cannot exist. So whenever there is a magnetic positive charge, definitely there will be a magnetic negative charge. So sum of the charges will be always 0. That's why it's become 0. So this in detail we doesn't have in our syllabus. It is beyond our scope of our syllabus. That's why we didn't discuss it now. Okay, so just remember it as Gauss's law for magnetism. Then Faraday's law. Faraday's law, as you discussed in chapter 6, closed integral E dot dl is equal to, closed integral E dot dl is equal to d phi E by dt. Closed integral E dot dl is equal to d phi by dt. That is Faraday's law. Closed integral B dot dl is equal to minus, there should be, according to Lenz's law, we have to give the negative sign too, right? So minus d phi by dt. And what is Ampere's Maxwell law? What is all we have discussed just now? This one. So Ampere's Maxwell law is closed integral B dot dl is equal to mu 0 IC plus mu 0 epsilon 0 d phi E by dt. So this is what is Ampere's Maxwell law. So in this equation, the 4 equations are there. So you can know that this is Gauss's law for magnetism, electricity, and Faraday's law, Ampere's Maxwell law. All the laws are given by some other scientists, but it is collected by Maxwell, and as it is known as Maxwell's equation, 4 important Maxwell's equation, and detailed analysis of this equation is beyond scope of our syllabus. So in higher classes, some of you have move into the path of physics later in future courses. So in that case, you will be learning detail about this equation. Okay, so now we doesn't have any details. I just mentioned it. Okay, so important properties of displacement current. So look at the properties. So displacement current exists whenever there is a change of electric flux. There should be change of electric flux, and like in steady condition, it will not occur. In steady current case, whenever there is a steady current, there is no scope for displacement current. Displacement current occur only when there is a changing electric flux. There should be a time varying electric flux. There should be a time varying electric field. Then only there will be a displacement current. Okay, so it does not exist in under steady condition. Under steady condition, it will not occur. Now, magnitude of displacement current is equal to the rate of displacement of charge from one capacitor plate to another. Okay, so the magnitude of displacement current will be directly proportional to the displacement of charges from one capacitor plate to another. Okay, then together with the conduction current, displacement current satisfy the property of continuity. So a circuit should be closed only if the charge flow should be closed, right? The charge flow should be through a closed path, and in that circuit what you have seen here is the charge flow is made completed by the property of displacement, by making use of displacement current only. So the continuity of this charge flow is made fulfilled by displacement current. That is the last property. Third property is saying together with conduction current, displacement currents is make satisfies the property of continuity of current. Okay, so we have just mentioned it. It's not important even though. Okay, so then next section of the chapter, electromagnetic waves or EM waves. EM waves. Do you have an example for EM waves? So in exam, as I mentioned, it's better to write electromagnetic waves itself. Don't go for the abbreviation EM waves. Okay, so we can use it for class purpose only. Okay, so EM waves. Can you give any examples for EM waves? Put it in the comment box. Can you put any example for EM waves? Yes. What is EM waves? So this is just introduction for EM waves. So we can directly move to the definition. Okay. Whenever, as I mentioned, whenever there is a changing electric flux, there will be a magnetic field. As I mentioned. Okay. So whenever there is a changing electric flux, it will be creating a magnetic field also. Whenever there is a changing electric field, it will be creating magnetic field. Okay, so this electric field, changing electric field, let's just like a, not just like a wow, just like a wave. Okay, so whenever there is a changing electric field, this changing electric field will be also producing changing magnetic field also. Changing electric field producing changing magnetic field. That is what I have discussed earlier, right? So this disturbances, electric field disturbance and magnetic field disturbance is having a property of wave, and that is what is known as electromagnetic wave. So this is the concept. Changing electric field producing changing magnetic field. So there are some more additional property that can be added to it, and for now just understand that. So changing electric field producing changing magnetic field. This will be having a property of electromagnetic disturbance in wave in air on in the medium, and have the property of a wave. So that wave is known as electromagnetic wave. Okay, so the variation in electric and magnetic field vector, whenever there is a variation in electric field vector, it will be producing a magnetic field vector. Whenever there is a change in magnetic field vector, it will be producing changing electric field. Okay, so the variation in electric and magnetic field vector perpendicular to each other. It will be perpendicular to each other. Okay, so the electric field variation and magnetic field variation will be perpendicular to each other. That's why I have drawn it in two plane. If this is electric field, I have to draw the magnetic field just perpendicular to it. Okay, so in detail I will mention. Now you understand. Changing. Sorry. Yes. Yes. So perpendicular to each other leads the production of electromagnetic disturbances, electric field and magnetic field disturbances in the space, and this disturbance have the property of waves and known as electromagnetic waves. Okay, so this will be in the definition for electromagnetic waves for our syllabus. Okay, so the variation of electric and magnetic field vectors perpendicular to each other, it is the production of electromagnetic disturbances in the space, and this disturbance have the property to move from one place to another, or which have the property of a wave, and that waves are known as electromagnetic waves. Okay, so what are the source of electromagnetic waves? The previous year question. Okay, so oscillating or accelerating charge, a steady, as I told you, if a charge moving with a constant velocity, same uniform motion for a charge, it is steady current situation. Charge moving with constant velocity means steady current situation. In steady current situation, there is no production of varying electric field, which will not lead to the production of varying magnetic field. Okay, so there should be a non-uniform motion for the charge. Then only it is not called non-steady current. Okay, so the accelerated non-uniform motion means accelerated motion, right? So accelerated charge or oscillating charge. Oscillation means to and fro motion, right? To and vibration, to and fro motion. So this kind of to and fro motion of charge, to and fro, to and fro, to and fro. So this kind of to and fro motion of charge or accelerating charge. Acceleration charge means non-steady motion, non-uniform motion. Then only there will be variation in electric field. Okay, so oscillating or accelerating charge will producing electromagnetic wave. So what are the source of electromagnetic wave? It is the oscillating or accelerating charge. Okay, so we have to study in detail about the source in some other places. We can discuss it later in the end of this session. Okay, now then, so James Maxwell, the same Maxwell that you have discussed now. So Maxwell theoretically predicted the existence of electromagnetic wave, and even though he can't find any experimental proof for this electromagnetic wave, it was later found by some other scientists. So it was Maxwell who predicted the existence of electromagnetic waves. Okay, and one more point we have skipped is this electromagnetic wave is transverse in nature. It's not a mechanical wave. It is transverse in nature, transverse wave. You already learned about longitudinal wave and transverse wave in your lower grade itself, grade 9. Okay, so in grade 9 physics, you are studying with transverse wave and longitudinal. What is transverse wave? The particles in the medium are vibrating. If there is a medium, even if the wave is propagating through a medium, the particles in that medium will be vibrating perpendicular to the direction of propagation of wave. That is transverse wave. And what is longitudinal wave? Particles will be vibrated parallel to the direction of vibration. Sorry, direction of movement of wave, direction of propagation of wave. Particle will be vibrating direction in the direction of parallel to the direction of propagation of wave. And example for longitudinal wave is sound wave. And transverse wave means particle vibrating perpendicular direction of wave. So here electromagnetic waves are transverse in nature. It is another previous year question, I think. Yes, another. So what is the nature of electromagnetic wave? Transverse, longitudinal, like that. So it is transverse in nature. Okay, so James Clerk Maxwell theoretically predicted the existence of electromagnetic wave. As I told in the beginning, when we are starting about electromagnetic wave, I told you what do we have an example for electromagnetic wave? Light. The visible light is an example for electromagnetic waves. Okay, now as I mentioned, perpendicular vibration will be leading to the production of electromagnetic waves. So here, this is a representation of electric field, and it is in the X plane. Electric field vibration is in the X plane, as you know in the figure. Okay, then what about magnetic field? It should be perpendicular to that. So that's why it is given like a slanting. Okay, so it is in the Y plane. Electric field is in X plane and magnetic field is represented in Y plane. You can give a slanting for that one. So wait, there is a slanting, then only you can easily represent it. So if electric field vector you have mentioned like this means you have to give a slanting for magnetic field vector. Then fill it with some vertical columns, then only the diagram will be complete. So it is an asked question, previously asked question. So give the representation of electromagnetic wave. So this is the representation of electromagnetic wave. So you can give the slanting like this, and for electric field it can be vertical lines. So representation of this one, just carefully look into the diagram in exam, carefully draw the diagram with a pencil and scale. Okay, so this is the representation of electromagnetic vector, which is a previously asked question. So there is not at all required that electric field should be in X plane and magnetic field should be in Y plane. It can be in any plane. And remember that if electric field is in X plane and magnetic field is Y plane, in the Y plane, direction of propagation of wave will be in Z plane. That's an important point. Electric field in X direction, magnetic field in Y direction, and direction of propagation will be along Z direction. Got it? And one more point, in every situation, electric field, magnitude of electric field will be more and that of magnetic field will be very less. even though in this representation the amplitude for each wave is given as equal, right? So it is not like that. It's just for a representation. In actual, electric field magnitude will be very very high and that of magnetic field will be very very less. Okay, so why so? I'll give an explanation for that. Okay, so not now, after 1 or 2 words. Okay, so magnitude of electric field will be always more and that of magnetic field is very very less in especially in the case of light. In light is an example for electromagnetic wave, right? So in light, electric field disturbances or electric field vector and magnetic field vector will be there, and out of which electric field vector have the more magnitude and magnitude of magnetic field vector is less. Okay, remember that one. So now we can give nature and properties of EM waves. Nature and properties of EM waves, which is very important one. Okay, so what are the nature? First one, electromagnetic waves. In electromagnetic waves, electric and magnetic field vectors are perpendicular to each other. That is very important one, and both are perpendicular to the direction of propagation of wave. Electric field vector and magnetic field vector are perpendicular to each other, and both of them will be perpendicular to each other. Very important point. Okay, so properties and nature definition of electromagnetic waves is very very important one. Don't skip any points. Okay, so first one, they are perpendicular to each other. What are perpendicular to each other? Electric and magnetic field vector, and both are perpendicular to direction of propagation of wave. Okay, so here, if electric field is in x direction, magnetic field is in y direction, obviously direction of propagation of wave will be x direction, z direction. Okay, if electric field is in x direction, magnetic field is in y direction, direction of propagation will be z direction. So if electric field is in positive x direction, magnetic field is in positive y direction, whether, as we mentioned, should be perpendicular. Direction of propagation of wave should be perpendicular. So whether is in positive is the direction or negative is the direction. How will be the direction? How can we give? So the direction of electromagnetic wave is given by, there is a relation. It will be always the direction of E cross B. Okay, so the direction of electromagnetic wave will be always be in the direction of E cross B. What is E cross B? Vector product of E and B. It is not B cross E, it is E cross B. How will you find the direction of E cross B? Using screw rule. Screw rule, you know, right hand screw rule, right hand screw rule, you know, to find the direction of vector product. It is, you have learned in grade 11 itself, and in 4th chapter we have already used it. Okay, so do you have confusion regarding that one? Means you can refer the video of 4th chapter. In that we have discussed in detail. Okay, so how will you find the direction of E cross B? By using screw rule. Okay, so the direction of propagation of electromagnetic wave is given by the direction of E cross B. Okay, it will be perpendicular to, for a vector product, it will be perpendicular. The resultant will be perpendicular to both the vectors E and B, right? So that is the first point. Remember this point. This using this one. This is a previous question. It is a previous year question. The direction of electromagnetic wave is given by E cross B, E dot B, something like that. Some more options are like that. Like the options are, I think, E cross B, E dot B, B cross E, and B dot E. So out of which, as I mentioned, it's a direct question, right? E cross B is the right answer. The direction of propagation of electromagnetic wave is in the direction of E cross B. Okay. Next one. Next property. The electric and magnetic fields are represented as, right? Electric and magnetic field vectors are represented as. Okay. So yes. So if electric field is in x direction, we can represent Ex. So electric field vector is in x direction, we can represent Ex. Ex is equal to, representation is E0 sine k z minus omega t. I will explain each term. And if magnetic field is along y direction, it is, representation is B0 sine of k z minus omega t. So here E0 B0 is the peak value, as you know, representation of waves. E0 B0 is the peak value. So, and here what you have mentioned is k. K will be equal to E0, B0 are peak values of electric and magnetic field vector, and K means it is also known as wave vector, which is given by 2 pi by lambda. Lambda is the wavelength. Okay, so which is known as wave vector. Wave vector. What is K? Wave vector. Okay, also known as propagation vector or propagation vector. Propagation is also known as propagation vector. Wave vector or propagation vector. So what is omega? Omega means its angular frequency. What is omega? Angular. Omega means angular frequency. And what is E0, V0? E0 and V0 are amplitude. Amplitude, that is what is peak value, right? So E0 and B0 are amplitude. So here you can see Ex, By, and here it is Z common, right? So here along with the wave vector or propagation vector, what is the which direction is mentioned? Z direction is mentioned. So which means the wave is along Z axis or Z direction. Wave is propagating along Z axis. So along with the wave vector or propagation vector, what is the symbol given? Z, which means the wave is propagating along Z direction. And one more thing, it is minus omega t, right? So Kz minus omega t means the wave is propagating along positive Z direction. What is it? The wave is propagating along positive Z direction is minus Kz minus omega t. Z means along Z direction and minus omega t means it is along propagating along the positive Z direction. So use this, there is a previous year question. So give the representation of electric and magnetic field which is propagating along negative Z direction. Give the representation of electric and magnetic field vectors in an electromagnetic wave in which the wave is propagating along negative z direction. If it is propagating along z negative z direction, the representation will be Ex will be equal to E0 sin kz plus omega t. So is it propagating along z direction and in the negative z direction, that's why it is kz plus omega t. Then magnetic field will be By is equal to B0 sin kz plus omega t. Okay, so this is the representation. So in which along negative direction it is propagating means you should mention plus, and if it is propagating along x direction means here along with the wave vector it should be x, and here it will be, if it is x it will be z and y respectively. Okay, so accordingly you have to make the changes by using your common sense. So this is a previous year asked question, so don't skip it, this is an important point. Okay, so this is the representation of electric and magnetic field vectors. Okay, next point, the ratio of electric field to magnetic field is a constant. The ratio of electric field to magnetic field is a constant. What constant? Okay, so E by B or E0 by B0, E by B, which is equal to, we can also written as E0 by B0. It's constant, and that constant is C. What is C? Speed of light. Speed of light. Speed of light. Speed of light means speed of electromagnetic wave. Okay, light is an example of electromagnetic wave. Okay, C is electromagnetic wave. Speed of light E by B, ratio of electric field to magnetic field vector is a constant E0 by V0, which is speed of light. Okay, so ratio of electric field to magnetic field is a constant. Don't write it B by E, which is wrong. E by B means you will be getting 1 by C. Okay, don't skip it, don't swap it. E by B will be 1 by C, and remember E by B. So that is why I told here C is a large number which is having the order of 10 raised to 8 meter per second, right? So that B should be, the denominator should be small, then only you will be getting a large number like this. Okay, then only you will be getting a large number like this. So E should be high and B will be small. In every electromagnetic wave, the magnitude of electric field will be high and magnitude of magnetic field will be less. So this is the reason I told you in the beginning, right? So the ratio of the E to B, electric field to magnetic field vector, is a constant. So this is a constant. So using this, there were questions, there were numerical questions. Okay. So using this equation, numerical question means it is a matter of substitution. You can arrange if electric field vector Electric field is given means you can directly find the magnetic field in that electromagnetic wave. Just multiply. Electric field is given means you can find the magnetic field. B will be equal to E by C. Just a matter of substitution. Easy, right? Then the velocity of electromagnetic wave through a free space is given by there is a small relation. What is the velocity of electromagnetic wave? Light is electromagnetic wave. So free phase means vacuum. What is the speed of light in vacuum? It is C, 3 into 10 to the power 8 meter per second. So it is given by, don't tell this is E by B, E by C, sorry, E by B. There is another relation, 1 by root of 1 by root of mu 0 into epsilon 0. What is mu 0? Permeability of free space. What is epsilon 0? Permittivity of free space. Okay. So velocity of electromagnetic wave through a free space is a constant, and that constant is C is equal to 1 by root of epsilon 0 into mu 0, or mu 0 into root of mu 0 into epsilon 0. If it is moving through a medium, for a medium, is the velocity of electromagnetic wave will be remain same? No, it will not remain same. So speed will be varied. So that will be equal to, not the same equation, corresponding permeability and corresponding permittivity. So velocity will be equal to 1 by root of mu 1 by root of mu into epsilon. Mu means permittivity of that medium, permeability of that medium, and epsilon means permittivity of that particular medium. Okay, you got important equation, very important equation. This is a previous year question too. So value of C is, some more options are there, you can select the exact option. Okay, so the properties of every properties of electromagnetic wave is asked as previous year questions. Okay, so very important one, don't skip any points, don't skip any points. Okay, so then they require no medium for propagation, they require no medium. So that's why light is coming from sun to the earth. There are some medium, there are a region in which no medium are present. Vacuum is the right, vacuum. So they can propagating through vacuum. VAC is vacuum, not VACCUM. It is VACUM. Okay. So they require no medium for propagation, so they can propagate through vacuum as well. So it shows reflection, refraction, interference, diffraction, polarization. All this phenomenon, as you know, as we have completed every chapter in grade 12. So polarization, you know, diffraction, you know, interference, you know, reflection, you know. So it is all these phenomena are formed given by light, right? So light is an example for electromagnetic wave. So electromagnetic wave shows reflection, refraction, polarization, dispersion, etc. Interference, diffraction. Okay. So they transport linear momentum as well as energy. So electromagnetic wave possesses linear momentum and energy. Energy, you know, light possesses energy. That's why light energy is getting, right. And what about momentum? So how a electromagnetic wave, light possesses momentum. Momentum is mass into velocity, right? Then how it is possessing momentum? Light have any mass? Okay. So explanation for that one is beyond the scope of our syllabus. That's why we didn't discuss it now. Okay. So it is beyond the scope of our syllabus. So just now for you can learn the property itself, the transport. They transport linear momentum as well as energy. Okay, but you follow. And when a electromagnetic wave is traveling from one medium to other, its velocity changes, its wavelength changes, and its frequency remains constant. Frequency remains constant. Remains constant. It's a previous year question. It is a previous year question. Whenever a light entering from one medium to another, its velocity changes. Obviously its velocity changes, its wavelength changes, and frequency remains constant. Okay, its frequency remains constant. Listen, previous year question, don't skip this point. Okay, then electromagnetic spectrum, it is the last topic of the chapter. Very easy, very easy, very easy one. And the thing that you have to remember from this is there is a table related to that. What is electromagnetic spectrum? What is electromagnetic spectrum? Spectrum. What is spectrum? Spectrum means all electromagnetic waves. So later in the beginning, all we know about electromagnetic wave is about the visible light, and later it was found X-rays, gamma rays are found, and later it is finished. Field. A series is filled. A series of 7 spectrum elements are there, and that spectrum series is filled with 7 electromagnetic waves. And first one is what we know about electromagnetic waves is only about visible light, and X-ray, gamma rays is found. Okay, so all the electromagnetic waves. What are the different electromagnetic waves that we know now? We can start with radio wave. Radio wave. Okay, radio wave. Microwave. microwave, infrared, visible light, ultraviolet, and after ultraviolet, X-ray and gamma ray. So these are the 7 elements in electromagnetic spectrum. What is electromagnetic spectrum? Arrangement of all the electromagnetic waves in a particular order, in the increasing order of frequency or decreasing order of wavelength. In the increasing order of frequency, from radio to gamma, frequency increases and wavelength decreases. As you know, when frequency increases, wavelength decreases. Frequency increases, wavelength decreases. Then only the velocity can be maintained constant. Okay. So arrangement of all the electromagnetic waves in the increasing order of frequency or decreasing order of wavelength is known as electromagnetic spectrum. As you know, there is no discrete separation between a radio wave and microwave. So it is we can mention a range from, it is not suddenly change from radio to micro or micro to infrared. So there is no discrete separation. The separation will be gradually. The gradual separation we can give it. Okay, what is mean by that? Radio wave have lowest wavelength, lowest frequency, and the frequency of microwave is greater than uh, frequency of microwave is greater than radio wave. So from radio to micro, it is not a sudden transition, it will be gradually transferred. Okay, so we can mention a range. So there is no separation, discrete separation between radio and micro or micro and infrared. It's a gradual separation. Okay, so remember that that's not important anyway, I have mentioned that. Okay, so radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma. So this is the order of increasing frequency, this is the order of decreasing wavelength. How can we remember it? So these are the order: radio wave, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. So if this order should be remembered, this order should be remembered. This order should be remembered: radio, micro, infra, visible, ultra, X-ray, gamma. So R, M, I, V, U, S, G. Okay, R, M, I, V, U, S, G. This code you can remember, or else I have a code. Rahul's mother is visiting Uncle Savi's garden. Rahul's mother is visiting Uncle Savi's garden. So Rahul, R, radio wave. Mother, M, microwave. Infra is infrared. V, visiting, visible. Uncle, UV. Saviors, X, X-ray. And garden, gamma ray. You got it? Easy trick, right? Rahul's mother is visiting Uncle Savi's garden. Rahul's mother is visiting Uncle Savi's garden. Okay, so radio wave, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. So what is the order? Radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma ray. This order should be by hearted. This order should be by hearted, and for by hearting it, we have a code right now. Right? Easy. Easy, 11 cc. Right? So radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma rays. Okay. So remember one thing. After infrared, visible light is there. Visible light means it is the only electromagnetic wave that is sensitive for our eye. It is the only electromagnetic wave that is sensible for our eyes. Human eye is sensitive for visible light only. And visible light consisting of how many colors? You may be mentioned that is 7 colors. Not only 7 colors, there are trillions of colors. And what you have mentioned is VIBGYOR. Okay, so we are specifying color: violet, indigo, blue, green, yellow, orange, red. But actually there are so many colors, not only 7 colors. It is not possible to segregate 7 colors. There are so many colors. So we can call it as VIBGYOR. Okay, remember one thing. It is not infrared, ultraviolet. It is not VIBGYOR, violet, indigo, blue, green, red. There is a problem while writing like that. So after infrared, it is red. After infrared, it is red. Okay, we can mention about the red. What is red? Yes. After infrared, it is red. And before ultraviolet, it is violet. So where is violet? Violet. Where is no violet? We can just with blue. Okay, violet. And violet, any other color? Yes. Violet, indigo, blue, green, yellow, orange, red. This is the order. Okay. So remember that. So even though you are going in this order, don't remember after infrared visible light is starting, and don't start with violet. After infrared, you have to start with red. Infrared. After, okay. So after infrared, you have start with red. After infrared, you have start with red. Okay. So remember that. Okay, so after infrared, you have to start with red, and before ultraviolet, you have to start with, so before ultraviolet, there is violet. So, which visible light have highest frequency? Highest frequency is for violet. Highest frequency is for violet. Highest frequency is for violet. So, gamma rays burst occurs in space and release energy equal to the entire history of humankind in 1 second. So, is it a question or what is he saying? Sir, please answer. Sir, what about value of x? Which x, man? I didn't get you. Okay, so Philip is commenting. What about value of x? Could you please explain what do you mean? What is mean by x? Okay, so if you are explaining in the comment box, means I will answer it. Okay, so remember for increasing this order, you can remember this one too. So here where we starting? Where we starting from here, 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 and suddenly what happened to it? Suddenly it increases its frequency. So on this side, right side highest frequency and left side lowest frequency. Right side highest frequency and left side lowest frequency. Then only you can remember it easily. Okay. So starting from radio and ends in gamma, right? So starting from left, left, and towards right, it become high frequency. Okay, so lowest frequency, highest frequency. Left towards in the left side, it is least frequency, and in right, it is highest frequency. And gamma ray is having highest frequency, and radio wave is having least frequency. And radio wave is having highest wavelength. Wavelength is more, and gamma rays is having least wavelength. Got it? So other than this, we have to remember about this table. This table is very important, and there are in every question paper, either in compartment exam or in any of the sets, there is a question paper that can be asked from this table. Okay, very important one, so don't skip it. So what are the table? It is about type of the wave, what is the wavelength range or frequency range. Wavelength and frequency range, it should be okay, so it should be by hearted. Wavelength range and frequency range, it should be by hearted, and their use and how they are produced. These are repeatedly asked question. So this is the last topic of the chapter, last table of the chapter. So even though it is repeatedly asking what, so radio wave, what is the main purpose of it? Is radio is used for communication, telecommunication purpose. Radio wave is used for radio and television communication system, and it is produced by accelerated motion of charges in conducting wire. This production, how radio waves are produced, how radio waves are produced, ask question, previously asked question. Okay, so why, what did that X-ray stands for? And I just gave a fact about gamma. Okay, so what he is saying is I couldn't follow him. So if it is possible for you, Philip, explain in detail. I couldn't follow what you are saying in the comment box. Okay, so used in radio. Radio waves are used in radio communication system and is produced by accelerated motion of charges. And micro, as you know, microwave, we are using microwave. Microwave oven, you are familiar with, right? Microwave oven, we are used for cooking items or making some food items. So we are using microwave, and in microwave oven we are using. Other than that, this one is very important. Radar system of aircraft. This is asked. This is asked for several times. Which electromagnetic wave is used for radar system of aircraft? It is microwave. You are very much familiar with microwave is used in microwave oven. Other than that, this is very important. Okay, so learn the two. And wavelength range, it should be also by heart from 1 millimeter to 0.1 meter. So it is produced by special vacuum tube. So give the method of production of microwave. It is produced by special vacuum tubes. That's point is stated. Okay, so infrared, as you know, infrared is also known as heat waves. Why it is known as heat wave? I'll explain the last session. Okay, last slide I'll explain why it is known as heat wave. So infrared is also known as heat wave. Heat waves. So heat waves. wavelength range is from 700 nanometer to 1 millimeter. Wavelength range is from 700 nanometer to 1 millimeter. So it is used in satellite, and in every remote control you can see there is a, yes, there is a remote. Yes, in remote control, in the tip of the remote, we are using infrared LED. Infrared LED you can see. So if you are pressing the remote, means you can see that this LED is blinking, not with your eyes. Your eyes are not sensitive to infrared. If you want to test it, means turn off your camera in the mobile phone and blink that infrared blaster into the camera. You can see that blink in the camera, not with your eyes. You can't see that infrared with your eyes, but with the help of a camera. Camera is sensitive for infrared. That is why CCTV. In CCTV, you can see that small LEDs are there. You didn't see that it is glown in any moment, but in night it will be glown, and your eyes are not sensitive for it, for that light, but camera's eyes is sensitive. That's why night vision camera is working. Okay, that's how night vision cameras are working. Okay, so infrared used in remote controls and earth satellite. That's very important. Okay, so which ray is used in earth satellite? It is infrared, and produced by hot bodies and molecule. Infrared is radio, sorry, infrared waves are produced by hot bodies and molecule. Very important one, very important one. How infrared waves are produced? It is produced by hot bodies and molecule. Okay, last one, visible light. Not the last one in this slide. Okay, so visible rays, and its wavelength range is from 400 nanometer to 700 nanometer, and you are studying this fact for from the last 3 years, right? From grade 10 onwards, you maybe understand that, you maybe learn that 400 nanometer to 700 nanometer is the wavelength range of visible light. So our eye is sensitive to visible light, and it is produced by electrons in atom emit light when they move from one energy state to another. That is what you have discussed in spectrum, hydrogen spectrum. When electron in the ground state is moved to another energy level, it will be producing light, right? So which, my question is, which do you remember, which spectrum series is belongs to visible light? Lyman Balmer series, Passion bracket fund, which one? Lyman Balmer, which one? Commented. Which hydrogen spectrum series is belongs to visible region? Which one? So Lyman Balmer Passion bracket fund, which one is that? Commented below. Okay, next one. Three more are there. Ultraviolet, UV. LASIK eye surgery, which is used in LASIK eye surgery and produced by inertial electrons in the atoms moving from one energy level to lower energy level. So this is ultraviolet region. It's already there in hydrogen spectrum. In hydrogen spectrum, like bracket fund series are lying in ultraviolet series. So it is main use is used in ultraviolet rays are used in LASIK eye surgery. And one more thing, water purification. You may be heard about water purification. In UV purified water, you may be heard in some water purifier. So ultraviolet rays are also used for purification of water. And other than that, the one of the previous asked question about UV rays is which electromagnetic wave is, or which electromagnetic wave is absorbed by ozone layer? What is that? Ultraviolet. Ultraviolet rays are absorbed by, ultraviolet waves are absorbed by ozone layer, right? So ultraviolet rays, so its wavelength range is from 1 nanometer to 400 nanometer. So LASIK eye surgery and water purification is the main purpose of use of ultraviolet rays. And X-rays, as you know, medical application, and it is produced by X-ray tube. So it is very easy to learn, right? X-rays, medical application, right question, and it is produced by X-ray tube. And gamma rays, not Vasco da Gama. Okay, so gamma rays for destroying cancer cell. Which electromagnetic wave is used for destroying cancer cell? That is gamma cell. Directly asked question, right? So production, radioactive decay of nucleus. In the last chapter, not semiconductor, before that nucleus chapter is there. In the last session of nucleus chapter, we are discussing about nuclear fission and fusion. So in that we have discussed about gamma rays. So gamma rays are produced in radioactive decay of gamma rays. Sorry, radioactive decay of nucleus producing gamma rays, and its wavelength range is from greater than 10 ratio minus 3 nanometer. Sorry, less than 10 ratio minus 3 nanometer. Okay, so this is about types, use and production of electromagnetic waves. So 7 electromagnetic waves are there. and their wavelength range, their use, their production, is very important. Frequency is also important. So learn the table entirely. Don't skip any point. Don't skip any point. You can expect a question from this either in any of the set. Okay. Okay. So it's almost 1 hour, cover 1 hour 10 minutes. We can discuss one or two questions and after that we can leave. Okay, electromagnetic wave of longest wavelength or lowest frequency. Which electromagnetic wave have longest wavelength and lowest frequency? Comment it, comment it. After once you comment it, we can wind up the session. Okay, so electromagnetic wave of longest wavelength. Longest wavelength means left side, right? Left side. What is left side? Rahul's mother. R. Radio wave. Radio wave. So it is radio wave. Command it fastly. Okay. Then electromagnetic wave of shortest wavelength. This will be opposite on the right, left side. Left side, what is? Gamma. Gamma rays. Okay. Electromagnetic wave. So highest energy. For highest energy, you can recall the formula. Is equal to h nu. As frequency is more, energy will be no. Which electromagnetic wave have highest frequency? Highest frequency for gamma. So gamma is having. Gamma wave is having highest energy. Gamma wave is having highest energy. This is a previous question. Okay. So electromagnetic waves used in radar. Radar. What is that? Microwave or infrared? Microwave or infrared? Which one? In radar, we are using microwave. Microwaves are used in radar. All electromagnetic waves have same velocity. What is that velocity? Velocity of light. What is velocity of light? Speed of light. Speed of light. What is that? In vacuum, it is having, light is not. Vacuum, it is having 3 into 10 to the power 8 meter per second. It's not it's an approximative value. It is actually 2.9 something like that. Okay, and we are approximated as 3 into 10 to the power 8 meter per second. And infrared waves also known as I mentioned, it's also known as heat waves. This is a previous last question. Infrared waves are also known as heat waves. Why it is heat waves? This is because water molecules present in any material readily absorb the infrared waves, and after the absorption, the thermal motion increases. Once the infrared radiations are absorbed by the molecules, the thermal motion increases. So, as the thermal motion increases, this will be increase heat of the matter, heat of the molecules. So, it will be heating of the surrounding, so that it is also known as heat waves. So, infrared waves is also known as heat waves. Infrared waves is also known as heat waves. Okay. Then electromagnetic waves used in LASIK eye surgery. What is that? Comment below. Which wave is used for LASIK eye surgery? Yeah, so it is ultraviolet rays. Okay. Then one more question we can discuss. SI unit of. After this we can wind up. Okay. So SI unit of epsilon 0 d phi by dt. What is SI unit of d phi by dt? It's not nice. D phi by dt. What is the SI unit of this quantity? What is this quantity actually? This quantity is equal to displacement current. We have discussed in the beginning. This quantity is displacement current, ID. What is the SI unit of displacement current? What is the SI unit of displacement current? So we didn't discuss about the SI unit. But what we have discussed is total current is equal to conduction current plus displacement current. What is the unit of conduction current? Ampere, as you know. Only two quantities which is having the same dimension. Same dimension means same unit can be added. Principle of homogeneity that you have learned in grade 11, first chapter, units and dimension, right? So only those quantities which is having same dimension or same unit can be added. So IC is added to ID, which means IC and ID have same dimension, which means they have the same unit. So dimension of conduction current, sorry, unit of conduction current is ampere. So that of ID means this one, right? Ampere. So what is the SI unit of epsilon 0 d phi by dt? It is ampere itself. Okay, so I think we can wind up the session. Is there any doubts in the comment box? Let me check. No. Okay, so thank you for watching. In the next week, we can come up with some more videos, and thank you. Happy learning.